Michael Stevens, and today I'll be talking about our fourth lab where we're going to be looking at a mass spring oscillator system. So, in this lab, we're going to observe the 2D motion of a mass spring oscillating system and then construct a computational model to see in order to compare the two. And then we're going to look at how Newton's second law and the energy principle plays out in this scenario. So, from Newton's second law, we can get two formulas. We've been over this a lot, so I just went straight to the position and velocity update formulas that we'll use to update the location of the spring and the mass over time. But what we're mainly focusing on is the energy principle, where we say that the change in energy is equal to zero, assuming that everything is in our system, meaning that no energy is lost. And in this case, that means that the change in potential energy of gravity and of the spring plus the change in kinetic energy is going to equal zero. And then each of those having their own corresponding formula as well. So in our experiment, we're going to release the mass attached to the spring at an angle, and then we're going to watch its motion. And from that, we have these two graphs of the x and y positions. And of course, like I said before, our system being the mass, spring, earth, air, pretty much everything. And then as well, we get our velocity in the x and y directions, and we use all of this to get our initial position and velocity vectors. And then also it was given that our mass has a mass of 0.402 kilograms. So now let's make this computational model. So first we establish the period by looking at the difference between the period times, the amplitude times, and then averaging them out. So I took 3 periods and then took the total time and divided it by 3 to find the period of 1.5177 seconds. Then we calculate the spring constant using the formula 4 pi squared times the mass over the period squared. And then we also find the relaxed length of the spring and then all the other stuff that we're going to need to find our potential energy of the spring down here. Now we're going to apply those initial conditions that we found before to our energy components, and then we're going to find the force of gravity in the spring in order to find the net force, so that we can then use that net force on our position and update velocity update formulas. And then we're also going to update the spring as well. And then we'll finally update the energy so that we can now plot all of this on one curve together. So for position, we have the experiment and the model plotted, and you can see that they're pretty close. The model just slightly has a higher amplitude than the experiment, and we'll get into why I think that is soon. Then our energy is very symmetrical, as you would suspect, and you can see that our total energy remains at zero for the entirety of the time, and then our potential energy is going at twice the rate of our potential energy. So some possible sources of error. The first one that is most likely the reason for why the computational model has a higher amplitude is because it doesn't account for drag, because drag is always acting in the opposite direction of motion, meaning that it would decrease the amplitude, which is what we saw in our experiment. So that is most likely what is happening. Also, the starting time, I was choosing it from the frames of the video, and so it could have been a frame or two off, which is very possible. So in terms of our energy change, our system does, it's okay within the bounds of the energy principle. It does not violate it because our change in energy remains at zero. And then in terms of periods, we see that whenever we measure our periods in terms of x, we get a period of 1.646 seconds. And for y, we get a period of 1.5177 seconds, which is the one that I used. And this one I used is because it accounts for the force of gravity, whereas x does not. So theoretically, the one in the y direction should be more accurate.